inspired by the Newton's law of gravitation, where the gravitational force is proportional to the product of masses and inversely proportional to the square of the distance between them. So this guy, Charles Augustin de Coulomb, suggested a similar formula for the electrostatic force between two charged particles, and that goes something like this.
The electrostatic force between 2-point charges is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them.
This sounds like Newton's law of gravitation. Newton should have sued Coulomb for plagiarism.
What are you talking about? You are accusing this innocent looking man of plagiarism? See, despite its striking similarities with the Newton's law of gravitation, this statement was arrived at after an independent experiment conducted by Coulomb. Coulomb took a torsion balance. So torsion balance, just a rod suspended by the center. At one end of the rod, he attached a charge sphere, and he brought another charge sphere close to this. So there will be a force of repulsion. This force was measured. Now he conducted the experiment again, but this time with the charge on one of the spheres reduced to half.
How did he measure the charge?
You got a point, because at the time of Coulomb there was no method to measure the actual amount of charge in an object. So he did something like this. He brought another similar uncharged sphere, and if these two spheres were made to touch each other, the charges would be distributed equally, right?
Equally. How?
Obviously by symmetry. See, these two are similar spheres made of the same material, same size, so there is no reason why you would expect one of the spheres to hold more charge compared to the other. See, for one sphere to hold more charge than the other, so that should have some special property, right? Like bigger size, distorted shape, something like that. But there is nothing of that sort here, so we expect that the charges are distributed equally. So the total charge on one of the spheres is reduced to half. Do you understand? So he conducted the experiment with a reduced charge, and he observed that the force between them is also reduced to half. And he repeated the experiment many times with the reduced force and reduced the distance between them, and finally he came up with the conclusion that the force between two charged particles is proportional to both the charges and inversely proportional to the square of the distance between them. So don't you dare say Coulomb took credits for Newton's works, will you?
I was just kidding.
Yeah, I know that. What do you think I was doing? So anyways, back to Coulomb's law. There are about 5 points in Coulomb's law that you should be familiar with for solving any questions related to Coulomb's law, and here is the first one. So here we write an expression for the force between two charged objects. See, these two are point charges. That means the sizes of these two objects are very small compared to the distance between them. At least from some distance they look like points. So they are so small that the geometry of these objects can be ignored. These 2 point charges are placed in vacuum or free space, not in any other medium. So when these 2 objects are placed in free space, the force between them is given by the statement of Coulomb's law. So that is, the force or the electrostatic force between these 2 charged particles. So that is proportional to Q1, Q2 divided by R square. Alright, Q1 and Q2 are the magnitudes of these 2 charges, and R is the distance between them. So this is the statement given by Coulomb. So force is proportional to the product of charges and inversely proportional to the square of the distance between them. But this is only the characteristic of the force, but now we will define it more quantitatively. So the same force Fe, now we will introduce a proportionality constant. So this can be called the electrostatic constant. So K multiplied by Q1, Q2 divided by R square. Alright, so this is the formula for finding the force between 2 charged particles. So that is called Coulomb's law. Alright, so now this is the formula that you have to remember. Alright, the value of K is given by, so that one, K equals 9 times 10 to the power 9. What is the unit of K? K can be written in terms of the other known quantities, right? So K can be written as F R square divided by Q1 Q2. So what is the unit of F? Newton. So Newton meter squared divided by Coulomb. So Newton meter squared divided by Coulomb squared. So that is the unit of K. So this value you are supposed to remember along with the formula. Alright. So this is the important formula for you to find the force between 2 charged particles. Alright. Yes. Now we'll also write the same formula in terms of a new constant. So this K sometimes is written as this value 1 divided by 4 pi epsilon 0. So we introduce a new constant here, epsilon 0. So if you do this substitution here, the same formula will become, so Fe equals 1 divided by 4 pi epsilon 0, same value here, Q1 Q2 divided by R square. Alright, so this is also formula that you can remember. So both these are expressions for finding the force between two charged particles. Alright, the epsilon 0 value is given by this 8.854 times 10 to the power minus 12. What is the unit of epsilon 0? See, this 4 pi does not have any unit. So K and epsilon 0 are like reciprocals of each other. So that means the unit of epsilon 0 is the reciprocal of the unit of K. So that means Coulomb squared, alright, per Newton meter square. So that is the unit of epsilon 0. Alright, so both these expressions are important. So we have to remember the formula in terms of K and also in terms of epsilon 0. Okay.
Why another constant? The first formula seems to be good enough.
See, this K as such does not have any physical meaning. It is just called electrostatic constant. But this epsilon 0 has a physical meaning. It is called the permittivity of free space. As we are finding force between charged particles in free space, we use permittivity of free space. So what is permittivity? So that is a parameter based on how effectively a medium can distort electric field. More about that later. So now we have two expressions for force between two charged particles, right? So this and this both are equally important. Alright, so now that is point number 1. The expression for electrostatic force between two charged particles in free space. Is that okay? Now that we've written the force between two charged particles in free space, obviously we need to write the force in a different medium, right? So now here a medium has permittivity epsilon. Now the force here is given by, so the same formula 1 divided by 4 pi, instead of epsilon 0 we use epsilon, that is the permittivity of that medium. Alright, for free space the permittivity is epsilon 0, that's what we used in the last case. So here the permittivity is epsilon, so 1 divided by 4 pi epsilon. So the rest of the things same. So Q1 Q2 divided by R square. Alright, so for different medium, so we have to use different formula for force. Alright, so this epsilon is the permittivity of the medium. Alright, now we'll also write this epsilon in terms of a new variable. This epsilon is a varying value. It is a variable for different mediums. So this epsilon is also written in terms of a new variable. So this epsilon can be written in terms of, this is the permittivity of any medium. So that can be written in terms of the permittivity of free space multiplied by a new variable we introduce here, so that is epsilon r. Alright, so this epsilon r is called relative permittivity. It is also called dielectric constant. So epsilon can be written in terms of epsilon 0 and the permittivity, the relative permittivity of that medium. Alright.
Yet another variable to complicate our life?
See, we introduce new variables not to make things more complicated but to make it more convenient. Take for example the permittivity of olive oil, which is approximately 26.55. If you observe, this value is close to 3 times 8.85. 8.85 is the permittivity of free space. So permittivity of olive oil is 3 times the permittivity of free space. This 3 is what we call by the name relative permittivity. So tell me, is it easier to remember the permittivity of olive oil, which is 26.55, or simply the relative permittivity, which is 3? Alright, so to make things easier, we introduce this relative permittivity. In most of the cases, the permittivity of any medium is written only in terms of the relative permittivity. Is that okay? So now that we have written epsilon in terms of epsilon r, so that can be substituted here if required. Alright, now we will find the ratio of the force in a medium. So F in a medium divided by the force in free space. We know that the force in a medium and the force in free space, the difference here is only that epsilon value. So 1 divided by 4 pi epsilon 0 Q1 Q2 by R square, force in free space, and instead of epsilon 0 here we have epsilon. So if you do the division, so you will get epsilon 0 divided by epsilon. The rest of the terms get cancelled, but this epsilon 0 divided by epsilon, so that is what is written as 1 by epsilon r. Alright, so that means the force in any medium can be written as force in free space divided by this epsilon r. So this is one relation. Suppose you know the force in free space. Now we can find the force in any other medium using this formula if you know the relative permittivity of the medium. See, for a free space, this epsilon r value is always equal to 1. correct? Because epsilon is same as epsilon 0, so the relative permittivity value is always equal to 1. But if you take any other medium, so this value will always be greater than 1. So remember, epsilon r is greater than 1 for any other medium. So if you take this formula, so force in a medium, so that equals force in free space divided by epsilon r. You tell me which of these forces is smaller. So force in a medium or force in free space? Yes, so obviously force in a medium is smaller because this value is the force in free space divided by epsilon r, but that epsilon r is greater than 1. So that means force in free space is the maximum. So in any other medium, the force will be reduced. Is that okay? So these are the points that you have to remember, alright, related to force between charged particles in a different medium. So that is our point number 2, and now we will get into the next point. When we said force between two charged particles, we were only talking about the magnitude of the force, right? The expression k q1 q2 divided by r square only gives the magnitude of the force. But now we need to write the force along with the direction, because force is a vector. So now when we say force between two charged particles, are we talking about the force exerted by q1 on q2 or q2 on q1? It doesn't matter, both are same. As per Newton's third law, the force exerted by q1 on q2 or force exerted by q2 on q1 both have the same magnitude. Alright, so that means it doesn't matter. Force between two charged particles is simply the magnitude k q1 q2 divided by r squared. But now when you say the direction of the force, now we need to know whether it is force exerted by q1 on q2 or q2 on q1. Alright, suppose we want to find the force exerted by q1 on q2. So this is denoted by this symbol F21. So that is the symbol we use to denote the force experienced by this charge q2. Alright, this is the force on the charge 2 due to the first charge. Is that okay? So that has magnitude. So the magnitude is known from Coulomb's law, k q1 q2 divided by r square. So this is only the magnitude. Alright, so but we also need the direction of the force. So what is the direction here? So that vector, the unit vector, we need to take the unit vector, because magnitude is already taken into account. You only need the one unit vector along that direction. So that vector is denoted by r. Okay, r cap. R cap is the unit vector, which means one unit vector. How to find the unit vector? You find a vector along the force, divide by its magnitude. So that is how we find the unit vector. Alright, so this can also be written as this equals k q1 q2 divided by, so this vector which joins 1 to 2, okay, q1 to q2, so that is denoted by r21, right? That is denoted by r21. So that r is r21, that is that length, the magnitude of that vector. So r21 squared multiplied by this r cap. So r cap is r21 cap. Do you understand? So this is the unit vector along the direction of the force. But how to find r cap? Divided by, so r21 squared multiplied by, so how to find the unit vector? So you multiply the vector, divide that vector by its magnitude. Alright, divide the vector by its magnitude, so that will become a one unit vector. So this will give you the value k q1 q2 divided by r21 cube multiplied by r21 vector. So this is the force on the charge 2 due to the charge 1. Is that okay? So this formula, you need not remember this as a formula. Alright, so just you have to remember the concept. To find the vector along the force, you have to just remember the magnitude of the force. So that is known from Coulomb's law, and multiply by the unit vector. Okay, so this need not be remembered as a formula, just remember the idea. Simply multiply the magnitude of the force by the direction. What is the direction? The unit vector along that force. Alright, so simply remember the idea, so that will do the job, right? Now, so this is the formula for the force exerted by one charge on the other, so along with the direction of the force. Is that okay? Right. So here, instead of two charges, we have three charges, q1, q2 and q3. So q1 will experience force due to q2 and also due to q3, but it is given that the force due to q2 on q1 is independent of the presence of the third charge q3. Whether the charge q3 is present or not, the force between q2 and q1 is not affected. So that is what is the principle of superposition. Alright?
Yeah. That sound obvious.
It's not that obvious. As we know, the presence of a different medium can affect the amount of charge. Why not the presence of a third charge? That is also very much possible. See, this is not very obvious. So there's no proof for this, but experiments are consistent with this idea, so we just take it for granted. Alright, so we need to find the force exerted by both these charges Q2 and Q3 on the charge Q1. Alright, now we have seen that from this statement, these forces are independent of each other. So we just find the vector sum of these two forces. So the force experienced by the charge Q1, so F1 vector, so that is simply the vector sum of these two forces. Force on 1 due to 2 plus force on 1 due to 3. Separately we can add, because one does not depend on the other, we can add these two forces separately. Do you understand? So this idea can be extended to any number of charges. Instead of 3 charges, if you have 5 charges, you can find the force exerted by all the 4 charges on that one charge by the same idea, finding the vector sum. Not just the magnitudes, we have to add the vectors. Do you understand? So this is called the principle of superposition. So that is the force exerted by many charges on one charge. So that is the vector sum of all these forces. Okay. See, this expression for the electrostatic force is very much similar to the gravitational force, right? So there are a lot of similarities. So like both these forces are central forces. They act at the center of the object, and also both are conservative forces. There are a lot of similarities. But let's look at some of the differences. Gravitational force and electrostatic force. Can you tell me some of the differences between the gravitational force and the electrostatic force?
Gravitational force is only attractive.
Yes, gravitational force is always attractive. Alright, gravitational force is always towards each other, right? Whereas the electrostatic force can be both attractive and repulsive. So depending upon the nature of the charge, see, if both the charges are of same nature, both are positive, both are negative, so it is a repulsive force. But if both are they are of different nature, like one is positive, the other one is negative, so that is an attractive force. So it can be both attractive and repulsive, whereas the gravitational force can only be attractive force. Okay, so is there any other difference that you can think of?
G is independent of medium.
Yes, the gravitational force is independent of the medium. So electrostatic force is dependent. Alright. So as we know, the gravitational force constant G is independent of the medium. It is called universal gravitational constant for some reason, right? So G is constant everywhere in the universe, but whereas K is not independent of the medium. K depends on medium, or this epsilon, right? So that is the permittivity of the medium. So electrostatic force is different on different mediums, right? So that is one difference. Anything else? One more thing. So this gravitational force is usually considered a weak force against the strong electrostatic force. Why gravitational force is called weak force? What is the value of G? So G is 6.67 times 10 to the power minus 11. So very small value. But the K value, the electrostatic constant, is 9 times 10 to the power 9. So there is a huge difference. So that's why we call this electrostatic force a strong force compared to the gravitational force, which is considered weak.
But these forces work on different parameters. Can we compare their strengths?
Even I have this doubt. It's not logical to compare two things which work on different parameters. The gravitational force depends on the masses of the objects, and electrostatic force on the charges of the object. So it's not wise to compare these two things. When you consider objects of very small scale, like the subatomic particles, the electrostatic force between them is much stronger compared to the gravitational force, because the masses of these objects are very much negligible. But if you compare objects of macroscopic scale, like things we see around, most of these objects that we see around are uncharged, which means no electrostatic force between them, only gravitational force between them. And if you consider objects of astronomical scale like sun, earth and moon, there is no electrostatic force at all, only gravitational force is dominant, right? So but still we call this gravitational force weaker compared to the electrostatic force. That is because, see, when you take two objects, see for example these two objects, so these two objects have certain amount of gravitational force between them, so this force cannot be increased or decreased. At a certain distance the gravitational force is constant, but we can charge them enough to make the electrostatic force much stronger compared to the gravitational force. Do you understand? Is it possible or not? So in that sense we can make electrostatic force much stronger compared to the gravitational force. So that's why we call the electrostatic force strong, okay, or stronger than the gravitational force. Is that okay? Right. In addition to that, there are also other differences, like the gravitational force always follows Newton's law of gravitation, whereas the electrostatic force does not obey Coulomb's law in many cases. When the objects start moving, Coulomb's law fails. Only when the objects are at rest, Coulomb's law can be applied effectively. Einstein proved that even Newton's law of gravitation fails in many cases, right? So that is not the discussion here. So these are the important differences between the gravitational force and the electrostatic force. Alright, so now we are done with our theoretical discussion on Coulomb's law. Now we will start solving questions based on all these rules. Now here is a list of all formulae that we have discussed so far. Two objects are rubbed against each other. One of them loses 500 electrons. These two objects are kept at a separation of 30 cm. The electrostatic force between them is. When two objects are rubbed against each other, they get charged by friction, don't they?
What if they were both conductors?
Conductors cannot be charged by friction, of course, but it is given in the question that one of these objects loses a few electrons, so that means it gets positively charged, right? These electrons will get into the other object, so that gets negatively charged. So both these objects are charged now. That means we come to understand that they are not both conductors, alright? So these two objects are charged now. So we'll have to find a charge on these two objects like Q1, Q2, and the distance between them is also known from the question. So now we need to find the force between these two objects using Coulomb's law, alright? So let us find the charge on each of these objects. Right. So the first object has lost 500 electrons. So that means, so this has a deficit of electrons. So here the protons outnumber electrons by quantity 500. So this 500 is the value of n. So do you remember the charge of an object is n times E. N is the difference between the number of protons and electrons. So n is 500. So 500 multiplied by charge of a proton. So that is E. So 500 times E. So that is the total charge on the first object. See, on the other hand, so that object has gained 500 electrons. So now electrons there outnumber protons by quantity 500. So 500 is the value of n again, and 500 multiplied by the charge of an electron. So that will give you the total charge of that object. So Q1, Q2 are known, the distance between them is known. So we'll have to find the force between them using Coulomb's law. So this is a simple question based on the direct formula of Coulomb's law. Alright, yes. Charge on each of these objects, right? Charge on each of these objects. So that equals n times E. So n is 500. So 500 multiplied by the elementary charge E. So that is the charge on the first object. So the second object is negatively charged. So that has charge 500 times minus E. So either the charge is plus 500 or minus 500 times E. Alright. So now let us calculate this value. 500 multiplied by the charge of the value of E, which is 1.6 times 10 to the power minus 19. Okay, so that is 5 times 1.6, that is 8 multiplied by 10 to the power minus 17 Coulomb. So we found the charges on these two objects, right, like Q1, Q2. So the distance between them is given in the question, so we have to simply use Coulomb's law. So the force between these charged objects, right, the electrostatic force is given by the formula. So K Q1 Q2 divided by R squared. Alright.
We don't use the other formula containing epsilon 0?
See, the value of K is very simple, right? 9 times 10 to the power 9. Alright, so epsilon 0 value is 8.854 something, and that too, it comes in the denominator, and we also have to multiply 4 pi. It gets very complicated, right? For simple calculations, we use this formula only, K Q1 Q2 by R square. In some specific cases where it is absolutely required, so we use that epsilon formula. Alright, so in most of the cases for calculations, we simply use K Q1 Q2 divided by R square. Alright, so now Q1 is the charge on one of these objects, so that is 8 times 10 to the power minus 17, and similarly Q2 is the charge on the other object, so minus 8 10 to the power minus 17, So this whole value divided by, so r squared, r is the distance between them, it is given to be 30 centimeter. So we have to convert that into meter, right? Multiply by 10 to the power minus 2. So that squared. Alright, so let us do the calculation here. So 3 squared is 9, so 9 gets cancelled. So that will be, so 8 times 8, that is 64, multiplied by 10 to the power, so minus 34, so 25, 2, so minus 23. So that is 6.4 multiplied by 10 to the power minus 22 Newton. So this is the force between these two charged objects, right?
You dropped the negative sign.
See, the negative sign here doesn't really mean much, as we have not assigned any sign to a particular direction. So do you know which direction is positive, which direction is negative? No, we have not assigned any such sign. So even if you get Fe value negative, still we don't know the direction of the force F. Alright, so the negative sign here only means that the force between these two objects is attractive, not repulsive. As these two charges are of opposite nature, so the force between them is attractive. So that's what this negative sign means. But it does not give you the direction of the force F. Alright, so usually to avoid all this, we take the modulus of this, right? So we only need the magnitude of the force. So to find the magnitude of the force, we just find the modulus. I need not have taken this negative sign. Alright, so for magnitude, you just take the positive value of the whole expression. Alright, so this 6.4 times 10 to the minus 22 Newton, that is the magnitude of the force between these two charged objects. So suppose the question is to find the force exerted by one object on the other, then it makes sense to talk about the direction of the force, right? Suppose we want to find the force exerted by this object on the other. So then the direction of the force will be here, right? This direction, because the force is attractive, so it will be in this direction. Now the force exerted by that object and this object will be in this direction, so towards that object, right? So then it makes sense to talk about the direction of the force. But when you say force between two objects, there is no direction, so we just need the magnitude of the force. So that is what this value is. So we just need the magnitude, which is 6.4 times 10 to the minus 22 Newton, and that is the answer to the question, right? The mass of a proton and an electron are 1.67 times 10 to the power minus 27 kilogram and 9 times 10 to the power minus 31 kilogram respectively. The diameter of a hydrogen atom is 1 angstrom. If X is the ratio of the electrostatic force and the gravitational force between the proton and the electron in the hydrogen atom, and V is the speed of the electron in its orbit, then alright, so what's given here is a hydrogen atom. So hydrogen atom, it's a very simple setup. So just one proton in the nucleus and one electron in the orbit. So we need to find the force between these two particles. Not only the electrostatic force, we also need to find the gravitational force between them. So gravitational force can be found using Newton's law of gravitation, right? And the electrostatic force can be found using Coulomb's law. So that ratio is what is asked in the question. So let us find this ratio. Alright, so let us find both of these forces and divide. Yes. So X here is given to be the electrostatic force divided by the gravitational force. So this ratio is what is given as X. So Fe is K Q1 Q2 divided by R squared. Similarly, and Fg is the Newton's law of gravitation, right? So which is G m1 m2 divided by R squared. Okay, so now this R squared gets cancelled. So let us substitute the value of K, which is 9 times 10 to the power 9. And Q1 is the charge of a proton, which is the elementary charge is 1.6 times 10 to the power minus 19, and Q2 is the charge of the electron, so that has the same value, only the magnitude, right, divided by G. So G value is 6.67 times 10 to the power minus 11. Yes. And M1 is the mass of the proton, which is given to be 1.67 times 10 to the power minus 27, and also M2 is the mass of the electron, which is 9 times 10 to the power minus 31. So these are the values given in the question. So just do the calculation. So 9 gets cancelled, and then 1.6 squared. So 1.6 squared, so that is 2.56 multiplied by 10 to the power. So this is minus 38, so 9, so it is minus 29 divided by, see, 6.67 multiplied by 1.67. So we need to do this multiplication. But instead of using the value of G to be 6.67, usually we write the value of G to be what? So 6.67 is approximately equal to 20 by 3, right? So this is easier for calculation. So use the value of G to be 20 by 3 times 10 to the power minus 11. Similarly, 1.67 has value. See, 0.67 is 2 by 3. Alright, so 2 by 3 has value approximately 0.67. So 1 plus 2 by 3 is 5 by 3. See, we can also directly multiply these two values, right? But I am using this values so that the calculation will be relatively easier, right? So multiplied by 10 to the power, so this is 5869. So let's do this calculation here. So 2.56 multiplied by, so 3 times 3, that is 9. So 2.56 multiplied by 9. So that is approximately, so 23 multiplied by 10 to the power. So this is 2969. So 40, so 20 times 5, that is 100. So this is 10 to the power 38. 40 minus 2, okay? Yes. So this can also be written as, so 2.3 multiplied by 10 to the power 39, okay? So this is the ratio of the electrostatic force over the gravitational force, and that is the value of x. So that is the answer to one of these questions, right? Okay. See, but if you observe, the ratio of the electrostatic force over the gravitational force is of the order of 10 to the power 39. So this value is very huge. You understand, 10 to the power 39. That means compared to the gravitational force, electrostatic force here is much stronger between these two subatomic particles, right? So usually the gravitational force between them is ignored, right? Because you see, comparatively this value is much stronger. So gravitational force is so very small value compared to this value. So it is very insignificant, okay? So this is the ratio, and that is the answer to one of these questions. And now we also need to find the speed of the electron in the orbit, right? The electron is revolving around the proton due to a force towards the center. So that's what we call by the name centripetal force, right? So here the force acting on this electron is the electrostatic force, and that acts as the centripetal force. So let us find the centripetal force. What is the formula for the centripetal force? mv squared by r. Yeah. So that centripetal force here is due to the electrostatic force, which is K Q1 Q2 divided by r squared. Alright.
The gravitational force has no contribution to the centripetal force.
See, that's what we have understood from this. See, the ratio of the electrostatic force over the gravitational force is of the order of 10 to the power 39. So imagine how big this value is, right? So compared to the electrostatic force, the gravitational force is nothing. So it can be easily ignored, right? See, even if you add the gravitational force with this, will it have any impact at all? So it will have no significant difference, because this is huge value compared to this. If you add this tiny gravitational force, it doesn't make much of a difference. So you just consider the electrostatic force to be the centripetal force. Is that okay? Right. Now let us do the calculation. So from this we can get the value of V squared. So that equals, so K Q1 Q2 divided by mr. So this value is, K is 9 times 10 to the power 9, and Q1 Q2, so charge of the proton, and the electron is 1.6 times 10 to the power minus 19 squared, right? So both of these charges are same. Now the same calculation like we did here. M is the mass of the electron. So the mass of the electron is given to be, so 9 times 10 to the power minus 31, and r is the radius of the orbit. That means the radius of the hydrogen atom. But it is given in the question that the diameter of the hydrogen atom is 1 angstrom. So radius is half of that value, so 0.5 angstrom, that is the radius. But we need to convert that into meter, right? So what is the conversion? Do you remember? So 0.5 times 10 to the power minus 10. Alright, 1 angstrom equals 10 to the power minus 10 meter. So that is the conversion. So this is the value of r, so the radius of the hydrogen atom. Okay, so now if you simplify this, so this value is, so 9 gets cancelled, 1.6. So this is the value of V squared. So we need V value. So just take the square root. So that is 1.6 times 10 to the power minus 19 divided by, so this is 0.5, the square root of that. So 0.5 multiplied by, so 10 to the power 9. So this is 31, so 40. So 10 to the power 50. So if we take the square root, it will become 10 to the power 25. Okay, let us take the approximate values. So 1.6 divided by, what is square root of 0.5? See, we know the square root of 0.49, so that is 0.7, right? Because 7 squared is 49, so this value is very close to 0.49, so we can approximately take this value to be 0.7. So 1.6 divided by 0.7 or 16 divided by 7, so which can be approximately taken to be 2.2 multiplied by 10 to the power, so this is 6, that's it, so meter per second. So this is the required speed of the electron in the hydrogen atom. But we need the answer in terms of meter per second, no, kilometer per second. So we have to convert that into kilometer per second. So what to do? So 2.2 multiplied by, so let me write this value 10 to the power 6 as 10 cube multiplied by 10 cube, so meter per second. So that value is 2.2 multiplied by 1000, so that is 2200 and 10 cube, so 1000 meter. So 1000 meter can be written as kilometer per second. So that's it. So that is the answer to the question. So that's all. So this is the speed of the electron in the hydrogen atom, and this is the ratio of the electrostatic force over the gravitational force, and so that is the answer to the question. The force between two charges in free space remains same when they are placed in a medium of relative permittivity 1.44 with the distance between them reduced. The percentage decrease in the distances. So here in the first case, these two charged objects are kept in free space. So there is a certain amount of force between them. So in the next case, the same objects are kept in a different medium. So will the force increase or decrease?
Decrease.
So the force will decrease, right? So like we have seen already, so the force between charged objects is maximum in free space. Any other medium will reduce the amount of force, right? So but to compensate that reduction in the force, so the distance is also reduced. When the distance is reduced, the force will increase. So there is a balance. Alright. So what is the percentage reduction in the distance here, so that the force in the first case and force in the second case are equal? Alright. Yes. So let us calculate that. So we know the permittivity of any medium, epsilon, is given by the permittivity of free space, that is epsilon 0, multiplied by the relative permittivity. So we use this formula as this value is what is given in the question, right? The relative permittivity of the medium is given, so we'll use this formula later. So now the force in the first case is taken to be F1 and second case, so F2, but these two are given to be equal. So F1 is given to be equal to F2. So let us find F1, right, using Coulomb's law. So what is the force between these two charged particles? See, now let us use this formula. So 1 divided by 4 pi epsilon 0 q1 q2 divided by r square. So this formula is more relevant here because something related to the permittivity is given, so we use this formula. But in other calculations we use k q1 q2 by r square, right? So but because here it is required, so we use this formula. Alright, so this is the force in free space. Now we will write the force in a different medium, right? So that equals 1 divided by 4 pi epsilon, so that is the permittivity of the medium, so multiplied by q1 q2 divided by r square, right? But the distance in the first case is taken to be r1, so let us take that distance to be r1. So here in the second case the distance is r2. Okay, so let us simplify this. So most of the values get cancelled, q1 q2, so that gets cancelled, 4 pi. So what do you get? R2 squared divided by r1 squared, so that equals, so epsilon 0 divided by epsilon. So that value is, from this expression, epsilon 0 divided by epsilon is 1 by epsilon r. So this epsilon r is the relative permittivity of the medium, so that is given in the question 1.44. Alright, so this is the value of r2 squared over r1 squared. So let us take the square root. So r2 equals, what is the square root of 1.44? So that is 1.2, right? 12 squared is 144. So 1 divided by 1.2 r1. So if you do the division here, so r2 equals, so 1 by 1.2, so that is approximately, so 0.83 multiplied by r1. So now we have found the relation between these two distances, right? R2 and r1. But r2 is only 0.83 times r1. So that means r2 is less than r1. Right? By what factor? R2 is only 0.83 times, which means this is less than this value by a factor of 0.17, right? 1 minus 0.83 is 0.17. So the percentage reduction is this one. So there is a decrease in the distance. There is a decrease of 0.17 times. So that means it is 17%. You understand? So 17% is the reduction in the distance, so that the force in the first case, the force in the second case are equal, and that is the answer to the question, right?
We could have used the other formula which relates the permittivities of different mediums.
See, you mean to say this formula, force in a medium equals force in free space divided by the relative permittivity? See, we can't use this formula. See, this formula can be used only in situations where the difference between these two cases is only the medium. The rest of the things should be same. So like the charges are same, but the distance in the first case and the distance in the second case are not equal. So we can't use this formula. So this formula is only when there is only a change of medium. So the rest of the things should be same. So here the distance is also reduced. So we can't use this formula. So, but this itself is simple enough. Alright, so we can do this question by this method. Anyway, so the answer to this question is this one, 17% reduction in the distance, right? So that's it. The charges Q and 9Q are kept 12 cm apart. Another charge Q1 is placed at a distance x from Q such that the net force acting on any of these three charges is 0. Then, so there are two charges Q and 9Q placed at a separation of 12 cm. So there is a third charge, say Q1, which is placed somewhere so that the total force experienced by any of the three charges must be 0. So we have to place this Q1 in such a way that so the force experienced by that charge and also the other two charges must be 0. Alright, so obviously the charge Q1 must be on the line joining these two charges, right?
Can't it be somewhere else?
Can it be anywhere else? Suppose the charge Q is here and the charge 9Q is here. Can the third charge Q1 be somewhere here? So in that case, the force exerted by the charge Q will be in this direction, and the force exerted by the charge 9Q will be in this direction. So is there any chance of these two forces to cancel each other? So two forces or two vectors will cancel each other only when they are in the opposite direction and with the same magnitude. So these two random direction, so there is no chance of cancellation. Alright, so the only possibility is that the charge Q1 must be placed somewhere here, okay, between these two charges. Only then this Q will exert a force in this direction and this 9Q will exert a force in this direction. So there is a possibility of cancellation. Do you understand? So the charge Q1 must be here. Alright, so but where exactly, at what distance from this charge? So that's what we need to find. So suppose this distance is taken to be x. Alright, so this distance from the second charge, so that is taken to be y. We can take it as 12 minus x, right, because the total distance is 12 cm given, but I have taken this to be x and y. Now the force due to this charge and force due to this charge, so they should be of same magnitude, only then they'll cancel each other. They are already in the opposite direction, but magnitudes should be same. So let us find the force due to this charge and this charge, equate them. Alright, yes. So let's find the force on the charge Q1 due to these two charges, right? Force on the charge Q1. So this will exert a force in this direction. So we don't know whether this Q1 is positive or negative. So for now, let us take the charge Q1 to be positive. So if it happens to be negative, you will get the sign accordingly. So let us take Q1 to be positive for the time being, so this will exert a force in this direction, so positive direction. So what is the force? K Q1 divided by the distance x squared. Similarly, this 9Q will exert a force in the opposite direction. Alright, both are positive charges, so this direction. So tell me, minus K, so 9Q Q1 divided by that distance squared, so that is y squared. So this total force must be 0 as this experiences no force, so total force is 0. So let us do the simplification. So if you multiply, so we get x squared divided by y squared, so that equals, so 1 over 9. So that gives you the value x by y equals 1:3. So this is the ratio in which this point divides these two charges, right? See, x by y equals 1/3. Actually this can be generalized. Actually this ratio is actually square root of Q1 by Q2. Alright, so what is the ratio of these two charges? Q is to 9Q or 1 is to 9. So the square root of that is 1:3, and that is this ratio. So the ratio in which that third charge divides the line segment joining these two charges is the square root of the ratio of these two charges, right? 1:3. So you can generalize this and you can use it directly if required in questions. So x is to y here is 1:3. Okay, done. Now x value now. The total distance is 12. The 12 is divided in the ratio 1:3. alright, which means 1/4 of 12, so that is 3 centimeter. So that is the distance x. Similarly, this y value can be found, which is 3 times this 3, so 9 centimeter. Is that okay? So 3 plus 9, that is 12, and 1:3. So our required charge q1 is at a distance 3 centimeter from the first charge. Okay, alright, done. Now similarly we have to find the charge q1 also, the magnitude of the charge q1. Now we found the force on the charge q1. Similarly, we can also find the force on the charge q. Alright, because q also experiences no force. It is given that, so none of these charges experience any force. That means, so q also experiences no force. Do you understand? So the total force on the charge q due to q1 and 9q, so that must be 0. So let us find that also. So force on the charge q. So force on charge q due to this q1. So that will be in this direction. Okay, so let us take that, that is negative, right? So minus k q q1 divided by, so that distance is x, but x is already found here, so 3, so 3 square. And similarly, the force due to this 9q charge, so that will also have force in this direction. Alright, so both are of same nature. So now, so that is minus k q 9q divided by, so the distance, so this distance here is 12, right? The total distance is 12, so 12 centimeter, so 12 square. So this value equals 0. Okay, so simplify this, we should be able to get the value of q1. So k, q get cancelled, so q1 must be equal to, this is minus 9 times 9q times, so this 3 squared, so 3 squared is 9 divided by, so this is 12 squared, which is 144. So this will give you the value of q1. So that equals, so this is 16 times, so minus 9q divided by, so 16. So that's all. So that is the charge q1. So that happens to be negative, right? See, obviously it has to be negative. So otherwise, so if q1 is also positive, both these charges will exert the force in the same direction. So they'll not cancel each other. So the only possibility is that, so one of these charges must be negative. So q1 is negative, so that this will have force in this direction and this charge will have force in the opposite direction. So there is a possibility of cancellation. So we got the value of q1, which is the charge to be placed in the middle, so that the total force experienced by all the three charges is 0. Okay.
We don't consider the force on charge 9q.
See, we don't need to consider the force acting on the charge 9q because we've already got the answer required. See, instead of force on q, if you had taken the force on 9q, you would have got the same answer. So it is not required. See, by Newton's third law, the force experienced by these two charges is already 0. So that means these two objects will exert no force on the other object, right? Action reaction. So already this experiences no force. Automatically the force, the total force acting on the charge 9q will be 0. So we don't need to consider that. Just to confirm this result, you can do that, right?
What if one of the charges given in the question was negative?
That's exactly what we're going to do in the next question, okay? The charges 4q and minus 9q are placed at the points 0, 0 and 12, 0 respectively. The net force acting on the charge q1 is 0. The position of q1 is. So, unlike the last question, here we have two charges of opposite nature. One is a positive charge 4q, the other one is a negative charge minus 9q. These two charges exert no force on a third charge. So, we need to find the position of that third charge, right? Is it somewhere between these two charges like the last question? Suppose you place the charge somewhere between them, okay? Suppose here. Now, assuming this to be a positive charge and this is already a positive charge and that will exert a force in this direction. Alright, and this being a negative charge will exert a force towards itself in this direction. So both these charges exert the force in the same direction. So is there any chance of these two forces to cancel each other? No, because they are in the same direction. So that means we understand that our required charge is not placed between these two charges. So where else can it be? Let us try somewhere here. Suppose you place the third charge here. Now this is a negative charge that will exert a force in this direction and this is a positive charge that will exert a force in the opposite direction. So there is a chance that these two forces cancel each other. But this is a bigger charge, right? At least the magnitude. So this is a bigger charge at a closer distance. so that will exert more force compared to this smaller charge at a further distance. This is closer and also bigger. This is at a farther distance, but it is a very small charge. So that means, so these two forces will never cancel each other, because force due to this charge is bigger compared to force due to this charge. Though these two forces are in the opposite direction, the magnitudes don't match. So not here again. So where else? Maybe somewhere here. So this is a positive charge, so that will exert a force in this direction, and that is a negative charge, so that will exert a force in this direction. So the forces are in opposite directions. And what about the magnitudes? So this is a smaller charge at a closer distance. So this is a bigger charge but at a farther distance. So there could be a balance, right? So there may be some point here at which these two forces will be equal in magnitude, because this is a smaller charge but at a closer distance. So that is a bigger charge at a farther distance. So we can find some point here where the magnitudes of these two forces can be equal. Alright, so we understand that the position of the third charge is here. Alright, closer to the smaller charge. Alright, so now let us find the force due to both these charges and equate them. Alright, yes. So let's find the force on the charge Q1 due to these two charges. Alright, first let's find the force due to the charge 4Q. That force is in the negative x direction, right? Like, because these two are positive charges, so the force will be in this direction. So minus k q1 4q divided by the distance squared, but the distance is taken as x, so x squared. Similarly, the force due to the other charge, that will be in the positive direction, right? Because that is a negative charge, so attractive force, so positive direction, so plus. So now we take only the magnitude k q1 9q, so 9q only, just the magnitude, divided by that distance is 12 plus x, right? 12 is the distance between the given two charges, so 12 plus x squared, right? So this must be equal to 0, as we want the total force to be 0. Okay, so let us do the simplification here. So this will give you, so if you do the multiplication, this is x divided by x squared divided by 12 plus x squared, so that must be equal to, right? So this is 4q divided by 9q, that is 4 divided by 9. So that means we'll get x divided by 12 plus x equals 2 divided by 3. Alright, if you observe, this relation is similar to the last question. See, even in the last question, we got the ratio of the distances same as the ratio of the square root of the given charges. So the charges here are 4q and 9q, taking only the magnitudes. So the ratio is 4:9, the square root of the ratio is 2:3. The same ratio we got here also. The only difference here is that here it is external division, right? So the point where the charge q1 is located, so that point divides this line segment in the ratio same square root of q1 is to q2, but externally, not internally. That is the only difference. Alright, yes. Now we got this relation. So if you do the simplification, so 3x minus 2x, so that is x, so that equals 24. So 24 is the distance of the charge q1 from the charge 4q, but in the negative x direction. So the charge 4q is at origin, but this charge is at a distance 24 units from it, but in the negative x direction. So that means the position of this charge is minus 24, 0. So that's all. So that is the coordinates of the point where the charge q1 is situated, so it experiences no force due to the given two charges. So that is the answer to the question. 4 equal charges q are placed at 4 vertices of a regular pentagon of circumradius a. The total force due to these charges on the charge minus q placed at the center is. So it's a pentagon, right? 5 vertices. So 4 of these 5 vertices are occupied by 4 charges of equal magnitude q. Alright, and at the center there is a magnitude negative q. Now we need to find the total force exerted by all the 4 charges on the charge at the center. Okay, but these forces are in different directions. Alright, not in the same direction, so we can't simply add the magnitudes. So we have to add the vectors, the force vectors along these 4 directions. So then find the vector sum, so that will be the resultant force. Alright, but for this question we are not going to use that method. So instead we make use of the symmetry, right? So one vertex is vacant, right? Now you put another charge at that vertex, so you fill that vertex also with the charge of same magnitude. Now the pentagon is complete. Now can you tell me what is the force exerted by all the 5 charges on the charge at the center? That must be 0, right?
Why is it 0?
obviously, right, by symmetry. So consider these two charges, okay, so similar charges. Now you place a third charge in the middle. What is the total force? 0, because this will exert a force in one direction, so that will exert a force in the opposite direction, equal magnitude, so they cancel each other. So now we consider three charges of same magnitude placed at the vertices of an equilateral triangle. So you tell me what is the total force acting on a charge at the center? 0. So that is a vector concept, right? These two vectors add up to 0. So the total force is 0. So this idea can be extended to a polygon of 4 sides, right? Like a square, right? Equal sides. And similarly, a pentagon, a regular pentagon. Remember, all sides are equal. Otherwise, this may not work. So this idea can be extended to any polygon of any number of vertices as long as all the charges are of equal magnitude, and also the pentagon has all the sides equal, right? Regular pentagon. You understand? Okay. So now the force, the total force is 0. So force total, okay, the total force is 0. Do you understand? The total force. Total force means the force exerted by the 4 charges given in the question and the one charge that we have introduced. So the total force is 0. So what is the total force? So that is split into 2 parts. Force exerted by the 4 Q charges. You understand? The 4 charges given in the question plus the force exerted by the charge which we have placed there. So that force, this total must be equal to 0. Okay? Yes. That means the force due to the 4 Q charges, the 4 charges, so that must be equal to negative of the force due to the charge at the top. Okay? But we just need the magnitude. Okay? Let us only find the magnitude. So magnitude of the force due to the 4 charges, so that equals the magnitude of this, so that is Fq. Okay, so we don't need the negative sign, we just need the magnitude. So it is easy to find the force exerted by this one charge compared to the force exerted by all the 4 charges. So just find this. So both have the same magnitude. So this value is, so tell me, so K Q. So that charge also has magnitude Q. We are just finding the magnitude. K Q squared divided by, so the distance. So what is the distance? So it is given in the question that this pentagon has circumradius A. So what is circumradius? That is the radius of the circle circumscribing this polygon. Okay, so that means, so the distance between these two charges, so that is the radius, so that value is given as A. So this is A squared. Do you understand? So KQ squared divided by A squared, so that is our required answer, right? Force due to the 4 charges given in the question. Do you understand?
What is the direction of the force?
This direction can also be found using the same idea, right? So the direction of the force due to the 4Q charges is the negative of the direction of the force due to the charge at the top Q. Alright, so what is the direction of the force due to that charge? So these two charges are of opposite nature, so the force between them is attractive, so the force exerted by the charge Q will be upward, okay, towards itself. So that is an upward force. That means, what is the direction of the force 4Q? That is negative of that. So that means it will be a downward force. So the direction of this force will be downward. Anyway, that's not asked in the question, but anyway, the direction of the force will be downward, and the magnitude of the force is KQ squared divided by A squared. Alright, see, the direction of the force is very obvious, right? So from the geometry itself we can easily guess it, or we can use it, use this relation also. Okay, anyway, KQ squared by A squared, so that is the answer to the question, right? The charge Q is split into 2 parts and kept 2 meters apart, so that the force of repulsion between them is maximum. The maximum force due to these charges on the charge Q1 placed on the equatorial plane is. So there is a charge Q which is split into 2 parts and kept at a separation of 2 meters. Now we need to find the ratio in which this charge is split so that the force between these 2 charges is maximum. Alright. Not only that, so there is a third charge, the force exerted by these 2 charges on the third charge, that should also be maximum. Okay, so a lot of things to be done, but let us do it one by one. Okay, let us first find the ratio in which this charge is split into 2 parts so that the force between these 2 charges is maximum. Alright, so let us take the 2 charges to be x and q minus x and find the force between them and find its maximum value. Alright, so let's find the force between these 2 charges. So force equals k q1 q2 divided by r square, so which means x q minus x divided by r square. The distance is 2, so 2 square. So this is the force between these two charged objects. Now we need to find its maximum value. So to find the maximum value of f, okay, we denote this by f max, the maximum value. What is the method? So it is a quadratic expression, right? To find the maximum value of a quadratic expression, so there is a formula. Anyway, we will use the simplest method, that is calculus, right? So you find the derivative equated to 0. So the point where the function attains maximum value, there the derivative is 0. So let us find the derivative. So df by dx must be equal to 0 for the function to be maximum. So what is the derivative of this? So k divided by 4 multiplied by x times q, qx has derivative q, minus x squared has derivative 2x. So that must be equal to 0. So equating this to 0, we will get the value of x to be q by 2. So we got the first charge, that is q by 2. That means what is the other charge? So that is also q by 2. So that means we understand that for the force between these two charges to be maximum, so this bigger charge is to be divided equally. Alright, q by 2, q by 2. So that is when the total force between them is maximum. You understand? So the charges are divided equally. Alright, q by 2, q by 2. Okay, so now we need to find the force acting on the third charge q1. Charge q1 is in the equatorial plane. So that means the perpendicular bisector, right? Exactly in the middle. So at a distance x from the center. So we need to find the force exerted by these two charges on the third charge. Alright, but these two charges will exert a force of equal magnitude, as these two charges are of equal magnitude and they are at the same distance from that third charge. So which means the magnitudes of the forces exerted by these two charges are equal. Only the directions are different. So this q by 2 exerts a force in this direction, and that q by 2 will exert a force in this direction. So vector sum we have to find. So we have to find the force vector and we have to add them. So let us take the angle made by the force with the vertical to be theta. Okay, that means the force F1 has two components, one in the horizontal direction, one in the vertical direction. So we have to first find the horizontal direction. Okay, so what is the horizontal component? F1 sin theta for that force F1, and this force F1 also has a F1 sin theta in the opposite direction. So the horizontal components of these two forces cancel each other. F1 sin theta cancel each other. But vertical components add up. What is the vertical component? F1 cos theta, these two forces add up. So that means the total force is F1 2F1 cos theta in the vertically upward direction. So what is the force? So 2F1 cos theta in the upward direction, right? So 2F1 cos theta. So that is the total force. We want this force to be maximum. Alright, so let us first find the force. This is 2F1. So what is F1? So take any one of the charges. So force exerted by that charge q by 2 or this charge q by 2, because both are same. So let us find the force. So that is k q by 2, that charge q1 divided by the distance squared. So but what is the distance? So it is square root of, it's a right angle triangle, right? So use Pythagoras theorem. So this distance is 1 unit. So half of the total distance 2 units, right? 2 meter is the total distance, half of that is 1 meter, and the height is taken to be x. So that means, so using Pythagoras theorem, so that is x squared plus 1 squared. Alright, so we've used the formula k q1 q2 divided by r squared multiplied by cos theta. Cos theta can also be found using this triangle, as these two angles are equal. So in that right angle triangle, what is the value of cos theta? So that is the adjacent side, which is x divided by the hypotenuse, which is again the square root of x squared plus 1. Okay, so let us simplify this. So this is k q1 multiplied by x divided by x squared plus 1 3 by 2. Alright, so 2 plus 1 3, so 3 by 2. So this is our required force exerted by these two charges on the third charge. So we want this force to be maximum. So we'll have to follow the same method. You have to find the derivative, equate it to 0. But this expression here is little complicated compared to this one, but the method is same. How will you find the derivative of this? Do you remember the method to find the derivative of u by v, quotient rule?
v du minus u dv by v squared.
Yes, so that is the formula to be used. So let us find the derivative. So df divided by dx equals, so k q q1 multiplied by, so this derivative is So v squared in the denominator, so x squared plus 1 q, alright, multiplied by, so this v minus derivative of x is 1, so this derivative, so the derivative of this value is x multiplied by, this as 3 by 2 x squared plus 1 to the power 1 by 2 multiplied by the derivative of x squared plus 1, 2x, right, chain rule, x squared plus 1 has derivative 2x. So this value must be equal to 0, so df by dx must be 0. So let us simplify this, so we can multiply this, divide by these constant values. We can also divide by the common factor, which is x squared plus 1 to the power 1 by 2. So that if you do, you get x squared plus 1 minus, which is 2 cancel, so 3x squared equals 0. So 2x squared equals 1, so x squared equals 1 by 2. So we'll get x equals 1 divided by root 2. So that is the value of x, which means we have to place the third charge q1 at a distance 1 by root 2 from the midpoint. Okay, so that is when it experiences the maximum amount of force. Alright.
What about the other root of the equation? Minus 1 by root 2.
Of course, we should have taken the value of x also minus 1 by root 2, but it is not required because 1 by root 2 or minus 1 by root 2, so both mean the same distance from the center, right? 1 by root 2 is in the positive direction, minus 1 by root 2 is in the negative direction, so it doesn't matter. So we just take one of the values, because anyway the force at these 2 points will be same, only the directions are different. So just take one of the values, that is enough. So when x is 1 by root 2, that is when the charge q1 experiences the maximum amount of force. Alright, so okay, so now we've got the value of x. Question is to find the maximum force. So let us substitute this value of x here in this force, that will give you the maximum force. So our F max equals, so that value is k q q1. This x, if you substitute, you get 1 divided by root 2 multiplied by, so this is 1 by 2 plus 1, 3 by 2 to the power 3 by 2. So taking reciprocal, so that is 2 by 3 to the power 3 by 2. So that will give you the value. So this is 2 to the power 3 by 2, that is 2 root 2. So 1 root 2 can be cancelled. So 2. So 2 k q q1 divided by, this is 3 to the power 3 by 2. So 3 to the power 3 by 2 is what? 3 root 3. That's all. So this is the maximum force on the charge q1 due to the two charges q by 2 and q by 2. So that is the answer to the question. Okay. Two conducting similar spheres with charges q1 and q2 connected by a non-conducting wire are in equilibrium. If the wire is replaced by a thin conducting wire, the tension in the wire quadruples. The ratio q1 by q2 is. See, there are two situations given in the question. See, in the first case, the two conducting spheres having some charges, say q1 and q2, are connected by a non-conducting wire. So that means these two spheres are isolated. So there is no way charges can move from one sphere to the other, as this is a non-conducting wire. So the charges will remain the same, q1 and q2. So there is a force of repulsion between them, and the tension will try to prevent it. So the tension balances the electrostatic repulsion between these two charges. So the tension equals the force of repulsion between them. And in the second case, the non-conducting wire is replaced by a conducting wire. What difference does it make? Now the charges can move from one sphere to the other. Now because these two spheres are similar, so they'll hold equal amount of charge, right, by symmetry. So the charges now become q and q. Alright, but the system is isolated. The two sphere system is isolated. So in the first case, the total charge is q1 plus q2. In the second case, the total charge is q plus q. So by conservation of charge, q plus q, that is 2q, that must be equal to the charge in the previous case, that is q1 plus q2. So q1 plus q2 must be equal to 2q.
We don't consider the charges on the wire.
That's a good question, but it's important to read each and every word of the question. So it is given that it's a thin wire. So what does thin mean here? So the wire is so thin that it does not hold any charge or negligible amount of charge. So thin here means that, so the charge held by this wire can be ignored. You understand? So approximately the total charge on the sphere equals the total charge in the previous case, which is q1 plus q2. Is that okay? Alright, so let us find the tension in these two cases. So in the first case, the tension is taken to be T1. So T1 equals the electrostatic force between these two objects, which is K Q1 Q2 divided by R square. So this is the tension in the first case. Now similarly, let's find the tension in the second case. So T2 equals, so K. So in the second case, the charges are equal QQ. So that means KQ squared divided by R squared. Alright, it is given that the tension T1 and tension T2 are related. So in the second case, T2 is 4 times the tension in the first case T1. So here it is given that the tension in the second case T2 equals 4 times the tension in the first case. Alright, so just substitute the values here. So T2 here is KQ squared divided by R squared. So that equals 4 times, so this value K Q1 Q2 divided by R squared. Alright, so now, so these values get cancelled. So we'll get Q squared equals 4 Q1 Q2. Okay, now this Q, Q1, Q2 all are related, right? So Q equals Q1 plus Q2 divided by 2. So that can be substituted here. So we'll get, so Q1 plus Q2 divided by 2 square. So that equals 4 Q1 Q2. Alright, so let us simplify this. So what is this value? Q1 squared plus 2 Q1 Q2. This is 4. 4 times 4, 16. So 2 Q1 Q2 minus 16 Q1 Q2, that is 14 Q1 Q2 plus Q2 squared. So this is Q1 squared minus, so 2 Q1 Q2 minus 16 Q1 Q2, so that is minus 14 Q1 Q2 plus Q2 squared. So that equals 0. Alright, so this we have to solve. This looks like a quadratic equation, right? But not exactly, because there are two variables, Q1 and Q2. Alright, quadratic equation. So we want just one variable. So what you do is divide by this Q2 square. So divide by this Q2 square. So that will become Q1 squared divided by Q2 squared. This is Q1 divided by Q2 squared minus 14 times Q1 divided by Q2. Okay, plus 1 equals 0. Now this exactly looks like a quadratic equation. So we can take this to be some x. So x squared minus 14x plus 1. So that is a quadratic equation. So to find the solution of this, we can use the quadratic formula. So Q1 divided by Q2. Or you can do one substitution here. So Q1 by Q2 equals say some x or y. So that will be a quadratic equation. The solution of that is, so do you remember quadratic equation formula? So minus b plus or minus. So that means 14 plus or minus square root of this 14 squared minus, so 4 AC, 4 divided by, so 2. Okay, so let us simplify this. So Q1 divided by Q2, so that equals 14 by 2, so that is 7. So plus or minus, so this is 192. Alright, so that can be written as, yes, so that if you simplify 7 plus minus, so that is square root of 48, because 192 is 48 times 4, so that gets cancelled. So square root of 48, so that can be written as 7 plus or minus, so this is 48 can be written as 16 times 3, so that is 4 root 3. So that's it. So that is the answer. So whichever is given in the question.
Why are we getting two answers?
See, both these values are correct. So when you say Q1 by Q2, it can also be Q2 by Q1. So when you have the ratio Q1 by Q2 as 2, it can also be 1 by 2. Alright, because when you say Q1 by Q2, it will have one value, and Q2 by Q1 will have the reciprocal of the same value. Actually, these two numbers are reciprocals of each other. So 7 plus 4 root 3 or 7 minus 4 root 3. So both can be taken as the answer. You understand? So Q1 by Q2 is 7 plus 4 root 3, suppose. Then Q2 by Q1 will be 7 minus 4 root 3. So whichever is given, so that is the correct answer. You understand? So that's it. The total electrostatic force on the charge 2q at 4, 6 due to the charges q at 1, 2 and minus q at 4, 1 is. So here we need to find the total force exerted by two charges q and minus q placed at the points 1, 2 and 4, 1 on the third charge placed at the point 4, 6. So these forces are in different directions. So that means we have to find the vector sum of these two forces. So not only the magnitude, we have to find the force along with the direction. Alright, so let us find the vector. Yes, so let us find the first force, say F1. So F1 is the force exerted by the charge q at 1, 2 on the charge 2q at 4, 6. Alright, so let us find that force that is denoted by F1 vector. So that is, first let us find the magnitude. So that is k q 2q divided by the distance square. So the distance is the distance between the 2 points, right? So that has a formula. So square root of x2 minus x1 squared plus y2 minus y1 squared. So let us find the distance. So square root of 4 minus 1. So 3 squared plus 6 minus 2. 4 squared. So 3 squared plus 4 squared square root. So that is 5. So 5 squared. This is only the magnitude, but we also need the direction. So the direction of the vector is taken to be r cap. R cap is the unit vector along this direction. We've already written the magnitude. We only want the direction. So that means unit vector. So r cap. But how to find this r cap? So I would expect you to remember some basics of vector. So 2 points are given. So what is the vector joining these 2 points? Just the difference. Alright, see, first 4 minus 1, 3. 3 is the x component of the vector. 6 minus 2, so that is 4. 4 is the y component of the vector. So that means the required vector here is, first let me write the magnitude here, 2k q squared divided by 25 multiplied by, so that vector has x component 3, so 3 I cap, and y component 4 j cap. So this is the vector. So we don't need the vector. So we want the unit vector. So that means divide by its magnitude. So this divided by its magnitude, square root of 3 squared plus 4 squared. So that is 5. Okay. So this is the unit vector. This is the magnitude. So this is the force vector. Done. So this, if you simplify, we get 2k q squared divided by 125 3 I cap plus 4 j cap. Okay, done. So this is F1 vector. So force due to the charge Q. Done. Similarly, we'll find the force due to the charge minus Q placed at the point 4, 1. So that is denoted by, say, F2. So F2 vector equals, so first magnitude. So K, Q, I'm just taking the magnitude. Okay, so we don't take the sign. So just the magnitude, K, Q and 2Q divided by that distance. So that distance is 5, right? 5 squared multiplied by the unit vector along the direction of the force. So what is the unit vector here? See, these two charges are opposite in nature. That means it is an attractive force. So what is the direction of the force? So this charge minus Q will try to attract that the other charge, right? That means the force is in the downward direction. So that means minus j cap. So that is the direction of the vector, so downward vector, so minus j cap. You understand? So now we have to add these two forces, right? The total force we want. So F vector equals, so this F1 vector plus F2 vector. So just add these two vectors. So there are some common factors, 2k q squared divided by 125. So I'm taking that as a common factor, 2k q squared divided by 125. Here 3 I cap plus 4 j cap. Here this is just 25, but we have taken 125, which means 5 times this minus j. So minus 5 j cap. So that has value. So this is 2k q squared divided by 125 multiplied by, this is 3 I cap minus j cap. So this is the required force F vector. Alright, so that's it. But we just need the magnitude of this force. So that magnitude can be found 2k k squared divided by 125. That is a scalar. So I'm taking that out. So just find the magnitude of this force, 3i minus j. So that is square root of, so 3 squared plus 1, right? So that is 10. So that's it. So this is the required force. You understand? So the total force exerted by these two charges is the vector sum of the individual forces. So that has magnitude. So this value. Okay. So that is the answer to the question. A charge q of mass root 3 kg is suspended by a string of length 3 meter from the point A. If a charge minus q is placed at a distance 3 meter from A in the same horizontal level as A, the string makes an angle 30 degree with the vertical to keep q in equilibrium. The tension on the string T and the charge q are given by. So here a charged ball is suspended by a thread from the point A. What are the forces acting on this ball? The gravitational force is acting in the vertically downward direction and the tension in the vertically upward direction. These two forces balance each other, right? So this ball is in equilibrium. Now we put another charge minus q at the same horizontal level as the point A. So because of this charge, so there will be a force of attraction. These two charges are of opposite nature, so this force is attractive. Now this string gets deviated from the vertical position, making some angle 30 degree with the vertical or 60 degree with the horizontal. Now instead of two forces, we have three forces: gravitational force in the downward direction and tension in this direction, and also the electrostatic force between these two charges. So three forces act on this ball. Now the ball is still in equilibrium, so let us use the condition for equilibrium to find the tension on the string. Alright, yes. So we'll first find the electrostatic force between these two charges. So F equals, right, so K Q1 Q2 by R squared. But what are the charges here? Q and minus Q. We don't take the minus sign because we just need the magnitude. So K, Q and Q. So Q squared on divided by R squared. So what is R? The distance between these two charges. See, this looks like a triangle, doesn't it? See, this is a triangle with two sides equal. It is already given in the question that the length of the string is A and also that distance is A. So this is an isosceles triangle, and also the angle is 60 degree. Isosceles triangle with angle 60 degree. So that means, so this must be an equilateral triangle. Do you understand? All the three sides of the triangle must be equal. So that means the distance between the two charges, so that is also equal to the same A. So KQ squared divided by A squared. Do you understand? So this is the electrostatic force between these two charges. Alright, done. Now we'll use the condition for equilibrium. See, let's take only the horizontal components. Right, horizontal direction. Tell me, what are the forces acting in the horizontal direction? See, the component of the electrostatic force F in the horizontal direction, so that makes angle 60 degree with the horizontal, right? Alternate angle, so 60 degree. So the component of that force is F cos 60. Similarly, the tension also has a horizontal component that also makes angle 60 degree with the horizontal. So that has component T cos 60. So these two will balance each other because the ball is in equilibrium in the horizontal direction. So that must be equal to T cos 60 degree. So that will give you one equation. So F equals T. Alright. So this is one relation. Now similarly, we'll also find the vertical components. So take the vertical direction. So the vertical component of the force is F sine 60, right? F sine 60. Plus similarly, the tension has vertical component T sine 60. So that must be equal to the vertically downward gravitational force, right? So that equals mg. Alright, so that's all. Let's simplify this. So sine 60, so that is root 3 by 2. Alright, so I'm taking it out. So F plus T, that must be equal to m. So m is the mass of the object, so that is given to be root 3. So root 3 g. So g is taken as 10. Alright, so now we get another equation, that is F plus T. So that equals, so root 3 gets cancelled, so this is 20. So this is one equation. Alright, so we've got two equations, F equals T and F plus T is 20. We need the tension, so that means substitute this F value here. So 2T equals 20, so this gives you the value of tension, so that equals, so 10. So 10 Newton. So that's all. So that is the answer to the, one of the questions. Alright. Now we also have to find the charge Q. So let us find charge Q using this equation. So we have got the value of T, which is 10. So that means the value of F is also 10. So that can be substituted in that equation. So we've got the value of F to be 10. So that gives the value of this expression. That is 10 equals, so K value is 9 times 10 to the power 9 Q squared divided by A squared. So A value is given in the question, which is 3 meter, so that can also be substituted 3 squared. So that will give you the value of Q squared. So this gives you Q squared equals, so this gets cancelled 9, so 10 to the power minus 8. Okay, so that means the value of Q is 10 to the power minus 4. So 10 to the power minus 4 Coulomb. So that is our required answer. You understand? So this is the charge Q. Okay. Now we want to get the answer in terms of microcoulomb. So this can be written as, so 10 to the power minus 4 can be written as 100 times 10 to the power minus 6. Alright, Coulomb. 100 multiplied by 10 to the power minus 6, so that is 10 to the power minus 4. So that can be written as, so 100, so 10 to the power minus 6 coulomb. So that is what we write as the microcoulomb. Alright, so micro means 10 to the power minus 6. So 100 microcoulomb. So that is the answer to the question. So the value of Q. Okay. Two equal charges positive Q are placed at a distance 2b apart. Another charge capital Q of mass m placed in the middle is in stable equilibrium along the line joining the given charges. If Q is slightly displaced horizontally, it follows a simple harmonic motion with the time period t. Then here we have two equal charges placed at a separation 2b apart. Now we have a third charge capital Q placed exactly in the middle. So this charge Q is in equilibrium because the force exerted by these two charges are of equal magnitude but in opposite direction, because these two charges are at the same distance from the middle charge. So that means, so these two exert equal amount of force but in the opposite direction, so the net force is 0. So Q is in equilibrium. Is that okay? Now we slightly disturb this equilibrium position. See, we displace this charge Q by a small distance x. Now this charge now should have an oscillatory motion. So when will it have an oscillatory motion? Only when the force acting on the charge Q is towards the center. Alright, if the force is away from the center, so this charge will not be in oscillatory motion. So the force acting on this charge capital Q must be towards the center. So for that, what is the condition? So that is the first thing, and we also need to find the time period of the oscillatory motion. So shall we do it? We'll find the force due to both these charges. First of all, let's find the force due to the charge on the left. So that is given by, so K Q Q divided by R square. What is the value of R? The distance between these two charges. The total distance between the given two charges is 2b. So half of the distance from the center to this charge, so that is b plus x. So b plus x. Alright, this is the magnitude of the force due to the charge on the left. What is its direction? See, we are not given whether the charge Q is positive or negative. In fact, that is what we need to find. Alright, so initially we assume that the charge Q is positive. Let's see what happens. So if the charge Q is positive, both these charges are positive, that means it is a repulsive force. So the force will be in the positive direction. So this force is positive. Is it okay? Assuming that the charge Q is positive. Now, let us also find the force due to the other charge. So the other charge will exert a force in the opposite direction, because again they are positive charges, repulsive force, so opposite direction, right? Now minus K Q Q divided by that distance. Again from the center to that charge the distance is b minus x, because it is closer by distance x, so b minus x. Is that okay? So this is the total force exerted by these two charges. Alright, now let us do the simplification here. So K Q Q is a common factor, and then if you do the multiplication here, this is b squared minus x squared squared, and if you do the simplification here, b minus x squared minus of b plus x squared, so that will become minus 4bx, because b squared x squared get cancelled. Alright, so this is the force. Now we want this force to be negative. Why negative? Because only when the force is negative, that means towards the center, will there be an oscillatory motion. So we want the oscillatory motion, that means this force should be negative. Is this force negative? That depends on the charge Q, right? If the charge Q is positive, this total value is negative, because the rest of the values are positive. So if Q is positive, so this value will be negative. But if Q is negative, already there is a negative sign, so the total expression will become positive. So we don't want that. We want the total force to be negative. For that, Q has to be positive. So for the force F to be positive, so we need the charge Q, the force F to be negative. We want the charge Q to be positive. You understand? Force is negative, for that the charge Q must be positive. So that is the answer to one of the questions. Alright, the charge Q must be positive. Alright, done. Now we also have to find the time period of the oscillatory motion. So let us find the time period. It is given that the value of x is very, very small compared to the distance b, right? It is given that x is very, very small compared to the distance b. So that means b squared minus x squared value, right? B squared minus x squared value can be approximately taken as b squared only, because x is very, very small compared to b. So that means if you subtract a very small value, so that doesn't make any difference. So b squared minus x squared is approximately b squared. You understand? See, this x is very small. Otherwise, it will not be a simple harmonic motion. Only when x is very small, it is a simple harmonic motion. It will still be an oscillatory motion. For simple harmonic motion, x should be very small. Alright, so let us do the substitution here. So this is b squared squared, b to the power 4, here b, so that will get cancelled. So we'll have minus 4k q q, that b gets cancelled, so this is b q. Alright, so this is the force multiplied by x. Now you see, force is proportional to the distance. The force is proportional to the distance. So that is the concept of simple harmonic motion, right? So force equals, force is proportional to the distance. Now, instead of force, if you want, you can write the acceleration. So acceleration can be written as just divided by the mass of the object. So that is minus 4kq divided by mass m b cube multiplied by x. So do you remember the formula for simple harmonic motion? The acceleration for simple harmonic motion is given by minus omega squared x. Alright, the angular frequency. So a equals minus omega squared x. Just compare these two expressions, we will get the value of omega. Once omega is found, the time period of simple harmonic motion is given by 2 pi divided by omega. You understand? So just substitute this value of omega from this, you will get the required time period. So this is 2 pi square root of reciprocal. So this is m b cube divided by 4k q q. Alright. So if you simplify further, so this 2 will get cancelled, right? Square root of 4, that is 2. So that is pi square root of m b cube divided by this k q q. So that's all. So this is our required time period of the simple harmonic motion. You understand? So that is the answer to the other question. That's it. Two equal charges positive q are placed at a distance 2b apart. Another charge capital Q of mass m placed in the middle is in stable equilibrium along the equatorial plane. If q is slightly displaced vertically, it follows a simple harmonic motion with the time period t. Then see, this question is just like the last question. Instead of the horizontal motion, this charge q is displaced by a distance x in the vertically upward direction. So just like the last question, so here also for oscillatory motion, the force should be towards the center. That means vertically downward direction. Can you tell me whether the charge q is positive or negative?
Negative.
Why is that so?
Otherwise the net force due to the two charges will be in the upward direction.
So unlike the last question, the charge q here is negative for the oscillatory motion. Only then the force will be acting towards the center. So charge q is negative. Alright. Now here the force due to this charge or that charge, so that is not in the vertically downward direction. Alright. So it is in some direction making angle theta with the vertical. Now this force we have to take the vertical component of. You see, this will also have a horizontal component, F sine theta. This force also has F sine theta in the opposite direction, so they'll cancel each other. You understand? The horizontal components of these two forces cancel each other, so we don't need to consider them. So we only need the vertical component of these two forces. Alright, let us find the vertical component, that is F cos theta. And this force also F cos theta. So 2 times F cos theta, that is the total force acting towards the center due to these two forces. Alright, so let us find the force. So let's find the force due to, say, one of the charges. Let's find the force due to the charge on the right. So that force is given by K Q Q divided by the distance squared. What is the distance? See, it is a right angle triangle. So we can find the distance, that is the hypotenuse, using Pythagoras theorem. So let us find it. So this is square root of x squared plus b squared, right? B is the base length. Okay, total distance is 2b. So this length is b. So this square. Alright, now this is only the force in the direction towards that charge, but we want its a component in the vertically downward direction. So take the component, so that is cos theta. You understand? This is the vertical component of the force exerted by that charge on the given charge. Alright, now that's it. Now similarly, even this charge will exert the same amount of force. So let us take the vertical component of that. That is again F cos theta. Do you understand? So that means twice of this. Okay, both the charges exert the same amount of force. Take the vertical component. So F cos theta, F cos theta. So 2 times that. Alright, done. Now let's do the simplification. So this is 2 k q q divided by, this is x squared plus b squared. Cos theta, again cos theta can be found from the right angle triangle, so that value is x divided by square root of x squared plus b squared, right? Cos theta from the triangle. So this can be simplified now. So this is 2 k q q divided by x squared plus b squared to the power 3 by 2, okay, multiplied by x. So this is our required force, but we want this force to be negative. Alright, so for the oscillatory motion this force should be negative, but it looks like a positive expression, right? So when will this be negative? Only when q is negative, right? If q is negative, the whole expression will become negative. So for the force F to be negative, alright, this charge q should also be negative. Do you understand? So the charge q is negative, which we have already guessed that the charge q must be negative. Alright, see, as q is negative, so I will write this expression as minus 2kq modulus of q, alright, divided by x squared plus b squared to the power 3 by 2 multiplied by x. See, q is negative, so that means we can write minus of modulus of x, right? Modulus of x means you are making it positive, that means it will have a negative sign also. Do you understand? So minus of modulus is negative. So this is the expression for the force. Now just like the last question, see, this b is very big compared to the small value of x, so b squared plus x squared will be approximately, see, b squared plus x squared can be approximately taken to be b squared only, because x is very small, adding that with b doesn't make much of a difference, so this can be approximately taken to be b squared. Alright, so that means this value is minus 2kq modulus of q divided by, so this is b squared only, so b squared to the power 3 by 2, so that is b cube multiplied by x. So this is our required force, right? Or we can find the acceleration, right? So this is the force. Now we will write the acceleration. So the acceleration just divide by the mass of the object, so that means mb squared. That's it. So we got the acceleration. Now like the last question, so we have the relation acceleration equals minus omega squared x. So comparing these two, we can find the value of omega, and the time period of the simple harmonic motion is given by 2 pi divided by omega, so that is 2 pi square root of, so omega value, reciprocal of that is mb cube divided by, so this value 2kq modulus of q. You understand? So this is the time period of the required oscillatory motion, and that is the answer to the question. See, we can simplify this, so we can write this 2 divided by square root of 2, so we can write square root of 2, so that is pi, so 2 by root 2, so that can be written as square root of 2, so 2mb cube divided by k q modulus of q. So that's it. So that is our required time period of the simple harmonic motion. That is the answer to the question. Four charges q1, q2, q3 and q4 of same magnitude are fixed along the x-axis at x equal to minus 2a, minus a and 2a respectively. If a positive charge q is placed on the positive y-axis at a distance b greater than 0, 4 options of the signs of these charges are given in list 1. The direction of the forces on the charge q is given in list 2. Match list 1 with list 2 and select the correct answer using the code given below the list. So here we are given with 4 charges q1, q2, q3 and q4 having equal magnitude placed symmetrically on x-axis. Now we need to find the total force exerted by these 4 charges on the charge placed on the y-axis. Now the first case is when all the 4 charges are given to be positive. Now let us find. Now what is the force exerted by these 2 charges? So these 2 we are considering separately because these 2 charges are at the same distance from this charge. So these 2 are positive charges, they will exert force in this direction. You understand, repulsive force. The resultant of these 2 forces will be in the vertically upward direction because the horizontal components cancel each other. You understand? So the resultant of these 2 charges will be in the vertically upward direction. Okay, done. So same goes with the other 2 charges also. They are also positive, so they will have force in this direction. So the resultant will be in the vertically upward direction. So if you consider these two pairs, they have force in the same direction. So these two charges have force in this direction, and these two charges also have resultant force in the vertically upward direction. So the resultant of the forces due to these two pairs of charges, so that will be in the vertically upward direction. Do you understand? So the vertically upward direction, that means the positive y-axis, that is the direction of the resultant of these four charges in the first case when all the four charges are positive. Alright. Similarly, we have the next case where the charges Q1 and Q2 are given to be positive and Q3 and Q4 are negative. Now, let us find the force exerted by Q1 and Q4. Q1 is positive, so that will exert a force in this direction, right? So away from itself, and Q4 is negative, so that will exert a force towards itself. So this is the direction. So these two forces will have resultant in this direction. Do you understand? Because the vertical components cancel each other this time. So only the horizontal components will remain. So the resultant of the forces due to the charges Q1 and Q4, so that is in the horizontal direction. That means positive x-axis. Similarly, so we have the other two charges Q2. Q2 is positive, so that will exert force in this direction. And Q3 is negative, that will have force in this direction. So the resultant of these two forces will also be in the same horizontal direction. So the force due to this pair Q1, Q4 and force due to this pair Q3 and Q2, so they have the same direction, positive x. So that means the resultant of these two forces will be in the positive x direction. So that is the answer to the second part, right? Positive x direction. Alright. And the next case where the charges Q1 and Q4 are given to be positive and the other two are negative. Now the forces due to the charges Q1 and Q4 will be in these directions. So the resultant will be in the vertically upward direction, just like the first case. Now these two charges are negative, so they'll have forces in these directions. So that means the resultant will be in the vertically downward direction. Now tell me, what is the resultant of these two forces? One in the vertically upward direction, one in the vertically downward direction. So what is the resultant? Not zero, remember, because these two forces are in the opposite directions, okay, but they are not of same magnitude. So these two charges are closer to this charge, right? So that means these two charges will exert force of bigger magnitude, because closer charges exert more force compared to charges at the farther distance. So these two charges compared to these two charges are at farther distance. So that means, so the resultant due to these two charges, so that will be of smaller magnitude. The force due to these two charges is of smaller magnitude. That means upward force is of smaller magnitude compared to the downward force. So that means the resultant of these two forces will be in the vertically downward direction, not zero. Do you understand? So because these two charges exert forces of bigger magnitude and the other two will have force of smaller magnitude. So that means the resultant, the answer to the third case, so that is vertically downward direction, that means negative y-axis. Do you understand? So that is the next case. Now again we have the other case where Q1 and Q3 are given to be positive and Q2 and Q4 are negative. Now let us consider again Q1 and Q4. Q1 positive, so this direction, and Q3 negative, this direction. That means the resultant will be horizontal, positive x-axis. Okay, done. Now, so this charge Q2 is negative and Q3 is positive. So negative charge this direction and Q3 is positive this direction. The resultant of these two forces will be in the negative x-axis, like this. So one is in the positive x-axis, one is in the negative x-axis direction. So that means what is the resultant? Again not zero, because so these two are closer charges. So that means this force is of bigger magnitude compared to the force due to these two charges. So this is smaller force compared to this. That means what is the resultant? That will be in the negative x direction. Do you understand? So that means the resultant of all the forces due to all the charges is in the negative x direction. So that is the last case. Now we can choose the option that matches with what we have found. So we're done with our discussion on Coulomb's law. In the next class we'll be doing electric field. Bye for now.